Today I'm going to be talking about synthetic aperture radar imaging at the Coseismic and post-seismic deformation from the 2020 Southwest Puerto Rico seismic sequence. I've been doing this research in collaboration with colleagues at the University of Puerto Rico, Mayagüez, Elizabeth Vanacore and Alberto Lopez, and Uri Ten Brink at the U.S. Geological Survey in Woods Hole. Puerto Rico is in the plate boundary zone between North American plate and the Caribbean plate. There's a highly oblique convergence direction, so there's deformation on a number of faults, including the Septentrional fault to the west in Hispaniola and the subduction zone to the north in the Puerto Rico Trench. Faults within the island of Puerto Rico have activity of unknown age. Today I'm going to be talking about the 2020 earthquake in southwest Puerto Rico, where this star is located. This earthquake sequence started on 28th of December 2019 with a magnitude 4.7 earthquake, and then continued with some 5.0 and larger earthquakes until there was a magnitude 6.4 earthquake on the 7th of January in the same area, and which caused a significant amount of devastation in the local area of Guayanilla and southwest Puerto Rico. After the 6.4, there was a continued aftershock sequence and with a very long time history, including events well into the summer and even into this month, with magnitudes up to 5.8, much larger than we would typically see from a typical aftershock sequence. Elizabeth Vanacore presentation has more details on the seismic sequence. I'm going to be talking about synthetic aperture radar analysis that I've been doing using data from satellites that was collected with the synthetic aperture or SAR imaging mode. We do a next step of analysis, which is what we call differential SAR interferometry, or INSAR, to measure the distance change between the ground and the satellite on two different dates. As we can see in this diagram, if the object on the ground moves to a different position, there's a change in the range, or shown as delta rho in this case, between the two dates, and what we measure is the line of sight component of that ground displacement. We use data from the Copernicus Sentinel-1 satellite. There's actually two satellites, but they used just one satellite over Puerto Rico to acquire data approximately every 12 days. This first pair of images was acquired on the 9th of January and gave us the first look at the deformation from the magnitude 6.4 earthquake. We could see that there was a clear deformation to the west of the city of Ponce, but the rest of this image only covers the eastern part of Puerto Rico. The important thing to note is that the line of sight vector here, drawn as an arrow, shows that the line of sight direction is to the east, but it also includes up component. So that's what we are measuring with the line of sight INSAR. Here are two second images that were acquired over the area on the tracks that cover the southwestern part of Puerto Rico. These two tracks have the opposite look directions. The one on the left here, the line of sight direction is up and to the east, and the one on the right has the line of sight up and to the west. And you can see that even though these two interferograms are measuring the same deformation due to the main earthquake, the horizontal and vertical components add and subtract in different ways because of this different line of sight direction. We also got data from the Japanese JAXA satellite called ALOS-2 on January 20th. Japanese satellite uses a 24 centimeter radar wavelength as opposed to the roughly 6 centimeter wavelength of Sentinel-1. And the 24 centimeter wavelength gives us better coverage of the INSAR measurements in the areas of more heavily vegetated ground surface. This also has a line of sight direction that's up and to the east, so it's a combination of horizontal and vertical. On the top plot here is the regional view. We see the largely vertical subsidence over the area of the Guayanilla Bay. And on the lower panel, we see a stretched zoom of the area of the Punta Montalva, where the Punta Montalva fault cuts through the peninsula there, and apparently had approximately 5 centimeters of surface slip. And this is likely mostly horizontal motion. And as we can see, the horizontal motion of strike slip parallel to that fault is almost exactly in the line of sight direction. So the satellite is very sensitive to horizontal motion in that specific direction. The next type of a more advanced analysis is to take a number of interferograms for a whole time interval. Here I've processed 66 interferograms from the Sentinel-1 satellite track. This is the descending track with the radar look direction to the east and up. And there's 35 dates of acquisition between the 18th of July 2019 and the 10th of September 2020. By taking those 66 interferograms and combining them with a time series analysis package called MintPy, we can reconstruct the deformation on the individual dates. So this plot here is showing the cumulative deformation on each date. As you can see over here in the middle row, there's a sudden jump between the January 2nd image and the January 14th image, and that of course is the large deformation that was due to the magnitude 6.4 earthquake on January 7th. Note that we can't separate exactly when that deformation happened because the satellite is only taking an image every 12 days, but we can form a time series for a given point. Here in this lower panel, I've made a time series for a point on the west side of Guayanilla Bay, and we can see the sudden jump in the line of sight displacement at the time of the January 7th earthquake. You can also see that there's some level of noise that's due to atmospheric variations. One of the ways to minimize that atmospheric effect is to do a step function fit to the data from the time series, and I've done that for the time of large earthquakes in this area on the 7th of January, the 2nd of May, and the 3rd of July. Here are the step function estimates for the January 7th earthquake converted from the ascending and descending track. I've taken those ascending and descending line of sight directions and combined them to make estimates of the vertical component of deformation on this top panel and the horizontal component of deformation on the bottom panel. Because the radar satellites are looking primarily east and west, They're very insensitive to the north component of deformation, so this horizontal motion is almost entirely the east component. And we can see now that the subsidence in the vertical direction is centered on the Guayanilla Bay, and we can take this vertical deformation displacement map and make contours of it. And I took those contours and sent them to my colleague Uri Tenbrink, and he's plotted them on this map as red lines for the 5 centimeter contours. And then he compared that to a fault model that he made with a uniform slip on a rectangular fault at depth using the strike and dip from the USGS moment tensor. He had to make a adjustment to the rate direction to get it to fit the data, but he got a very nice fit to the contour lines. His predicted contours from the model are in blue lines that match very well with the red lines due to that are the measurements from the SAR. And that's for a fault with a top at 2 kilometers depth and a bottom at 10 kilometers depth, and average slip around 1.3 meters. Over here on the lower left is a field photo showing the subsidence, the permanent subsidence of over 20 centimeters that's caused some of the area of Guayanilla Bay to be permanently underwater on the coastline. So in conclusion, the main rupture was on this northwest dipping normal fault. There was additional deformation during the aftershocks that I didn't have time to cover here. We believe that surface slip on the Punta Montalva fault is likely to be triggered slip at a very shallow depth and not directly connected to slip at depth. The SAR time series analysis enables estimation of the displacements over time and better separation of the atmospheric effects from the earthquake signals. And NASA is working on a new radar SAR mission that will be launching in about 2 years from now, the NASA ISRO SAR mission or NISAR mission.